So I backed this up a couple slides from where we ended, is it just breaks down that basics of the humoral branch of our adaptive immunity. So some reminders, our adaptive immunity recognizes very specific invaders that gets in the body. It mounts very specific immune responses to get rid of it. And also, we develop some memory against those invaders so that hopefully when we encounter them again, our immune system remembers how to deal with them. The humoral immune branch that we got through last class uses B cells. And B cells, we've got millions of different kinds of B cells in our body, and each one of them has its own unique B cell receptor that looks like Ys. And then if it encounters, and again, those Ys, those B cell receptors on the outside, if those hands encounter whatever they're supposed to, whatever they're very specific for, if it encounters it, it is now an activated B cell. It will differentiate and change into a plasma cell. And then that plasma cell will churn out antibodies. And the antibodies look identical to the B cell receptor, which they're supposed to, because they have to be shaped to be able to recognize that very specific thing that activated them to begin with. And we talked the last time, like there are different, how they kind of hang out and how the body part changes on the antibodies can vary. So there's 5 classes of antibodies. But the antibodies target that pathogen for destruction in several different ways, like increasing phagocytosis or attracting a natural killer cell. But it targets it to get rid of that pathogen out of the body. Now, our benefit is that we do develop some, not a lot, we do develop some memory cells so that hopefully if we encounter that pathogen again, our immune system can do this a whole lot faster. Because activating B cells, differentiating them to plasma cells, and churning out antibodies can sometimes take up to 2 weeks before we get full maximum immune system response, which means you're sick for a while. If we can get this going faster, because a memory cell's like, well, I remember what to do, we can start churning out antibodies within a matter even of hours, full max antibody within usually a day or 2. Hopefully, again, to get rid of the pathogen before you ever even saw signs and symptoms of it. Now, the humoral branch only targets extracellular pathogens, which means today we're going to look at the cell-mediated branch, which then targets what? Not extracellular, intracellular pathogens. This is the branch that has to be able to look at our cells and be like, there's something inside of you that's not supposed to be there. So infected cells, they have to look at our cells and be like, you're just not a normal cell. There's something inside of you that's not supposed to be there, and I'm going to have to kill you and everything that's inside of you. So let me get to... Now, the cells that are used in the cell-mediated branch are T cells. T for thymus, that's where they matured. But there's more than one kind of T cells. B cells, yeah, I know there's millions, but B cells are B cells, even though they're all unique. T cells are different. There are actually 3 classes, or 3 types of T cells, I should say, but 2 classes of T cells. Let me get a second. We divide our classes of T cells into something known as CD8 and CD4. And you're like, oh, what does that mean? Well, anything that's considered a CD8 T cell recognizes MHC1 antigens. And this is going to go back to last Wednesday. Do you remember what cells in your body has MHC1 antigens on them? I'm going to write it up because I'm going to keep referring to these today too. You might have to look backwards in your notes. What cells in your body have MHC1 antigens on them? Look back in your notes. No idea what slide number it is. Because you guys got to know this today, or a lot of us is not going to make sense. All nucleated cells. What cells in your body aren't nucleated? Red blood cells. It's pretty much every single cell in your body. We're just going to go all cells in our body, but every cell in your body minus those little red blood cells. So every single cell in your body, minus those red blood cells, have an MHC1 antigen on them. And our CD8 cells, meaning they can literally look at any cell in your entire body and know if it's infected or not. What cells in our body have an MHC2 antigen on them? Antigen-presenting cells. Sometimes you'll just list it as APCs. Examples of antigen-presenting cells: dendritic cells, and even B cells. B cells that can, yes, mount the full humoral immune system to make antibodies can still present antigens to T cells. Again, these two branches, although they do their own unique things, can still work together. CD4 T cells only recognize cells that have an MHC2 antigen. Now, my black is like slowly dying on me. Different types of T cells. Again, there are three kinds. T cells all have a receptor on them. Just like B cells had a receptor, they looked like a Y with two hands to attach. T cells have T cell receptors. They just don't look like a Y. They just look like a straight little stick. So here's a T cell. The orange part is the T cell receptor. It just doesn't have the branching arms. It still has a site on it to bind an antigen. Again, it doesn't have two like the hands. It just has one. But the unique part about T cell receptors, and it doesn't even matter if it's considered a CD4, a CD8, it will only recognize epitopes, so small little antigen fragments. It will only recognize foreign objects that are associated with one of those MHC proteins, whether it's MHC1 or MHC2. Example, intracellular pathogen. One of the most common intracellular pathogens is a virus. Again, viruses have to get inside of our cells, hijack them to cause our cells to make more viruses. So if this is one of your cells in your body, whatever cell it is, it's just a normal one of your body cells, but it's infected with a virus. This T cell has to be able to look at this cell and say, you have a virus inside of you. And it does not have X-ray vision. It cannot see inside of the cell. However, a fragment of that virus will show itself. So this is a normal body cell. It has an MHC1 protein on it, because again, every single cell in your body, minus red blood cells, every cell in your body has an MHC1 antigen on it. Part of this virus will attach itself to that MHC1 antigen. So one of your T cells will see, oh, well, that shouldn't be there. That means there's a virus inside of it that's being presented on that MHC1 antigen. Otherwise, It cannot see inside of the cell. A fragment of that internal pathogen, virus or otherwise, has to be attached to that MHC1 or MHC2, depending on what type of cell it is, for the T cells to be able to see it. Again, these only are targeting intracellular pathogens. So they have to be able to see what's inside of our cells, and those things only present themselves on those outside MHC proteins. Now, 3 types of T cells. 2 groupings, depending on where they recognize. Do they recognize something on an MHC1, so any particular cell in your body, or do they recognize something on an MHC2? 3 types of T cells. Only one of them is considered a CD8, recognizes MHC1. They're called cytotoxic T cells, or we give it a big T for T cells and a little c for cytotoxic. Based on the name cytotoxic T cells, what do you think it does? What does cyto mean? You guys are so quiet today. Lymphocyte, leukocyte, monocyte. Means cell. Toxic? It's going to be deadly. So a cytotoxic T cell does what? It kills cells. A cytotoxic T cell, if I go back, that's what this is, it's going to be like, oh, there's a virus inside of here. I'm being shown it. What's it going to do to the cell? It's going to kill it. So when you have if you have a virus, if you have any type of viral infection, your immune system is going to kill every infected cell. It's going to kill the virus, but it's going to have to kill our own cells too. And you're feeling sick when that's happening. So the job of a cytotoxic T cell is to see any infected cell in our body, minus red blood cells. It can see any cell in our body that might possibly have something inside of it, and its job is to kill that cell. The only way to get rid of the pathogen is you got to kill the cell that it's hiding inside. The other 2 types of cells, because there are 3 T cells, are both CD4 that recognize MHC2. There is a regulatory T cell, big T, little r, and a helper T cell, big T, little h. The helper T cell you're going to see come up a lot coming up as we talk about how this whole branch works to kill. The helper T cell's job is to help. It helps monitor your cytotoxic cells. It even helps activate your humoral branch. It helps. Again, it's only going to recognize infected cells that have an MHC2 antigen on them. And what cells are those? Antigen-presenting cells. So cells that literally look at my antigen. Here, do something with it. And the helper T cells are like, oh, okay, I should do something about this. We are infected, and the immune system needs help. And maybe that's to help get these guys going and killing, or maybe it's to start activating T cells. Their job is to help get the whole thing going. Regulatory T cells, their job, I was going to say, is to kind of suppress the immune system. Sometimes our cytotoxic cells are too good at what they do, and they start to kill normal body cells that aren't infected. That maybe they just, oh, well, I see a cell in the body, and I don't think it's infected, but I'm just going to kill it anyways. Sometimes their job is to start killing cells that don't need to be killed. Regulatory T cells kind of suppress the immune system. Again, people that have autoimmune disorders, sometimes it's the regulatory T cells. They don't have enough of them, which means they're not regulated and keeping the whole system under control. Now, I will break this down. But again, T cells, they mature in the thymus. We've got 2 branches, CD4 or CD8 cells and CD4 cells. So again, anything that's considered a CD8 only recognizes that MHC1. Anything that's a CD4 only recognizes MHC2. Here's your antigen-presenting cell, example of a dendritic. Again, it's got long extensions. That's where the word dendrite comes from. Now, A cytotoxic cell, so your T cell that can recognize MHC1, your cytotoxic cells, once they're presented, once it sees this little structure on there, it becomes activated. It wakes up, it knows it has to do something. It will start to make more of itself. It will make clones of itself, and its job is to keep going and finding that little red circle, whatever it is, and start killing any cell that might be presenting that little red circle. It can also make memory cells of itself. Same basic idea. CD4 could only recognize anything being presented, so this little red square being presented on a class 2 antigen. Once it recognizes it, it's activated, it starts to make more clones of itself. Some of them might become memory cells, but otherwise we have a nice strong army to recognize the little red squares and go out and attack them. There's a little bit more to that, but it's the basic. It's just being presented and activating. Now, my question for you guys, if you are an antigen-presenting cell, which of these do you have on you? MCH2, is that it? Is it still a nucleated cell? Yes. So what else will it have? It still will have an MHC1. If you are an antigen-presenting cell, awesome. That's your job, is to present antigens. You have an MHC2 antigen on you, but you still are a nucleated cell. So this also is showing it's still an antigen-presenting cell. It still has an MHC1. So an antigen-presenting cell can literally wake up all of the T cells. I mean, that's the job. It's an antigen-presenting cell. It's like we're under attack. I need every cell like on duty to fight whatever it is off. Now, how the cells start to talk to each other. We've got lots of different types of T cells. We even have those B cells. And so cells need to chat. They need to talk. So they use proteins because they can't use phones, and call each other and say, hey, let's work together and do all of this. They have to use different types of protein chemicals. So different types of white blood cells, whether it's T cells, B cells, or other white blood cells, will start to secrete chemicals. Examples, an interleukin. The word inter means between, like an interstate is a highway that goes between two states, if you didn't know that. Inter means between. An interleukin, this just means any chemical that goes between white blood cells, because the leuco means white. So it's any chemical that allows one white blood cell to talk to another white blood cell. And there are lots of these, and I say chemicals, but not like bad chemicals, proteins. And you'll see it, that we abbreviate it to ILs for interleukins. You'll see it in some of my diagrams, little things being secreted from different cells called ILs. It allows white blood cells to talk to each other. An interferon is actually part of our first line of defense, but it allows cells to chat. An interferon is secreted by virally infected cells to warn neighboring cells that there's a virus present and they should arm themselves. Our cells do know how to arm themselves against viruses. It's not always effective, but they do know how to arm themselves. So interferons allow cells to talk. Growth factors is a chemical protein that stimulates the making of more white blood cells. Again, if you are fighting a big war, you want a big army, growth factors is stimulating your bone marrow to start churning out those white blood cells as fast as possible. The tumor necrosis factor is something that cytotoxic cells will start to secrete to kill tumor or abnormal cells. Again, our immune system is equipped to fight off cancer. Does it always work? No, not always, but it's one of the best ways that we're looking at new cancer research is how can we increase the immune system response. It's immunotherapy, using your own immune system to kill cancer, and it's super effective. And then chemokines, the word kine on there, or kin is for kinesthetics, means movements. Chemokines is any type of chemical that causes cells to move. This is important when we have any type of an infection in a certain area. If you got a splinter or a cut on your finger and it becomes inflamed, the cells in that inflammation area are going to send out chemokines, cause white blood cells to be attracted to that area. And so it causes cells to move to a particular area. And so the immune system, again, we've got lots of cells involved and they all have to be able to chat with each other. Now, the cell-mediated branch, we kind of have our basic three types of cells. Some of this I've already reviewed already, but cell-mediated branch, it really targets intracellular pathogens and abnormal body cells. And again, when I talk abnormal body cells, I'm talking cancerous cells. Your cell-mediated branch is meant to target that. The most common intracellular pathogen, I already said it, what is it? Most common intracellular pathogen in the body. Viruses are the most common intracellular pathogen. Viral infections are a whole lot more common than cancer, thank goodness. There are bacteria that can get inside of our cells as well. When we get into our bacteria unit in like a week or two, we'll talk about ones that can specifically hide. That would have to target our cell-mediated branch. So other things that it's effective against, again, bacteria-infected cells. There's your virus, your cancer cells, pretty much just any abnormal cell, any pathogen, whether it's a bacteria, whether it's a fungus that gets inside of our cells, whether it's any type of parasite that gets inside of our cells. Our immune system has the ability to see using receptors inside of our cells. Here's, I thought I had more on here. Here's showing an example. Here's one of our white blood cells with bacteria inside of it. And not because it ate it and it's just hanging out there before it gets digested. There are some bacteria that can get inside of our cells and reproduce and hide out. It's a wonderful place to hide if you're a bacteria. Now, activating our cytotoxic T cells. It's like a 4-step process, even though it looks less than that. The first part is we have to activate the cells, and we do that by presenting antigens. The DC up here stands for dendritic cell, which means that this is showing it's an antigen-presenting cell. It's an antigen-presenting cell. It does have MHC2 antigens on it, and it has MHC1 antigens on it. So the very first thing, we can't activate anything, we can't start anything without first presenting the antigen. Like, let's show it something, whether it's on an MHC1 or on an MHC2. If it's on the MHC2, then this is going to give us our strongest activation of cytotoxic T cells. As long as we're being presenting something with that MHC2, as soon as we present, we're going to start to get T helper cells activated, and they're going to start to differentiate because there's lots of versions of T helper cells. This is showing, for example, this is the T helper 1 cell. Again, it's a helper T cell. It helps. And that's its job. We're going to get the strongest activation of cytotoxic cells if we can first wake up and activate helper T cells. We can start to see where I said ILs, interleukins, means these are things that white blood cells secrete. I don't care that you know any numbers. That's if you want to go into cell microbiology and immunotherapies. But they're chatting. So one white blood cell is talking to another white blood cell using these interleukins. So this T helper cell, now that I've made it, it's going to cause cytotoxic cells to start to make more of themselves. It's not to say they wouldn't by themselves without this, but it takes them a lot longer, and we usually don't get as many memory cells. So it will start to say, okay, well, you need to make more of yourself, and not just make more of yourself, you need to start making memory cells. So we're going to activate cells, we're going to make T helper cells, and we're also going to start to make memory cells as well as activated T cells. Once we start to make memory cells, okay, fine, we've made that. We just start to make more and more cytotoxic cells. So we're kind of waking up everything by presenting antigens, making the T helper cells right away. start to make more cytotoxic cells, including memory cells, and then it's just self-stimulation. It's the clonality. Let's make lots and lots of active killing cells. So now these active T cells' job is to go out into the body and patrol for every infected cell that has whatever triggered them to begin with, some kind of virus or something. And it's going to kill all those cells. We have lots and lots of active T cells to go out and kill. Showing this, and again, different pictures. Again, we're going to present the antigen to a cytotoxic cell. We can also present it to the T helper cells to activate them. We get that making of not just cytotoxic cells, but also memory cells, and then the full-on self-stimulation, aka clonality, making lots and lots of cytotoxic cells. But before we start to make lots and lots of cytotoxic cells, works best if we have helper cells to trigger it all. So again, different picture, just written out step by step. Steps: present antigen, make helper cells, clonal expansion, meaning making more cytotoxic cells, including memory cells, and then just full on making lots and lots of killing cytotoxic cells. Now, the memory cells. So we can get memory helper cells, we can get memory regulatory cells, we can get memory cytotoxic cells. The memory cells for your T cells generally hang out in the body a lot longer than the memory cells that came from B cells. These memory cells can hang out in the body for months, if not years, even decades. And the memory cells become active upon subsequent contact with that original antigen, or the little red circle or the little red square. And those cytotoxic cells, as soon as they see that little red circle, that little red square, the thing they saw, 10 years ago, they become active and they start to make lots of cytotoxic cells. The T cells become a lot more effective and work faster than the first time you're exposed to something. Again, presenting antigens, waking up helper cells, making memory cells, making T cells, making lots of T cells. Again, it can still take a while. Memory cells can trigger it to make those cytotoxic cells a whole lot faster. Again, we have those regulatory T cells to prevent autoimmune disorders or your immune system attacking normal cells. When I say normal, not infected. So T cell regulation, the job of the regulatory T cells is to kind of suppress our immune system. Another thing that helps regulate it other than regulatory T cells, usually the cells, like your T helper cells, need an antigen-presenting cell to really activate it. Just doing the cytotoxic branch where T cells start to kill, it can happen. But it's usually not a super strong response and it takes a lot longer. It's when the T helper cells get activated to do it, that's when you get the biggest army. And so by having that checkpoint of let's activate helper T cells, also kind of regulates that immune system. Now, back to the humoral immunity that we covered last Wednesday. There's two ways that the humoral branch can work or be activated, not really work. T-independent or T-dependent. T-independent means the humoral branch does its thing without any interaction from T cells. It's called T-independent. It can do it without T cell interaction. It's going to do everything we talked about on Wednesday. It's going to see a foreign object. It's going to make plasma cells. It'll make memory cells. It'll make antibodies. It will get rid of that foreign object. And it can do all of this without any T helper cells, without any type of T cell regulation. It gives us the fastest response. It's like, well, we don't need any help. We'll just do it ourselves. It's a faster response, but a weaker. We generally don't make as many antibodies, and we generally don't make as many memory cells. And the memory cells and antibodies that we did make, because there's not as many, don't last very long. So its job is to let's get rid of that foreign object as fast as possible, but then we're going to forget about it. A T-dependent, specifically T helper cell dependent humoral immune system, which means the whole humoral immune system branch is going to happen with the help of T helper cells, which will be more effective when all the cells work together. It's always more effective. I need my pointer thing because I'm too short. I have it in my hand. I'm going crazy. Now, eventually we're going to activate B cells to make plasma cells to make antibodies. That part doesn't change, but it's the what activates the B cells can be different. So how can we do this whole humoral branch up here on the left with the help of T helper cells? So we have something foreign in the body. We know this are antigen-presenting cells, so they've got both MHC1 and MHC2. Our antigen-presenting cells are going to present that foreign object, I guess the little green triangle, they're going to present that foreign object to our T cells. Now, that will activate our T cells. It's an antigen-presenting cell. It's got an MHC2. We're going to activate our T helper cells. Again, the first thing when they activate a T helper cell, it becomes a T helper 1 cell. It's like the first cell that does most things. But they can differentiate into other types of T helper cells. Instead of just waking up, if a regular T helper 1, I'm going to draw it up here. A regular T helper 1 activates and get the cytotoxic cells going. That's its job. It's to help. It's wake up and start doing your job a little bit more. Let's make lots of memory cells. Let's make lots more of yourself. But it can change as well and become another type of T helper cell, and it can become a T helper 2 cell. There's different T helper cells. A T helper 2 cell can take that foreign object, that little green triangle, and it can present it to B cells. So we woke up the T helpers, it changed into a T helper 2 cell, and it's that T helper 2 cell is going to take that foreign object and it's going to activate a B cell. So B cells, and when we talked about them last Wednesday, they get activated by extracellular pathogens. It sees a bacteria, it sees something else that's in the body, and can do all of this. But a T helper 2 cell can also show it a foreign object and activate it. And once that B cell becomes activated, it will still go through all the normal stuff. Becomes plasma cells, makes memory cells, make lots of antibodies. The benefits of activating the humoral branch using the T helper 2 cell, there's all my steps, is that the memory B cells that are now made when this whole thing was activated by T helper cells, the memory cells last longer. And we generally get a lot more antibodies. Which means you're going to have a longer lasting immunity right away, as well as long term. You're going to have lots of antibodies to fight the infection and even kind of keep patrolling the body for a while, looking for any infections because it's around. But we also have memory cells that are going to last a lot longer. So doing the whole humoral immunity, if it just sees a bacteria, great, let's get rid of it, it's gone, but then we kind of forget about it. If you can wake up T helper cells and they activate the B cells, we have a long-lasting or longer-lasting immunity to them. Couple examples. For example, if you got food poisoning because you went to some restaurant and you got food poisoning, can you get food poisoning the next week too? Absolutely. In theory, or maybe 2 weeks later, immune system. But in theory, if you got food poisoning, that's something foreign in your body. You should be able to wake up B cells. You should be able to make antibodies, and you should never get food poisoning again. However, usually it's bacteria that causes food poisoning, extracellular pathogens. Our job is to get rid of it as fast as possible. that we generally don't make a lot of antibodies, we don't make a lot of memory cells, and you can get sick over and over and over again from the same object. But if it's something in the body that can wake up T helper cells, any of our T cells, especially if it's waking those T helper cells up to make the humoral branch occur, longer lasting immunity, this is generally when we start talking about people being immune to getting certain diseases. So when the two branches work together, always more effective, longer lasting memory. Just showing an example, if you got some, you got a cut on something and you got the bacteria that causes tetanus, it's a toxin, that toxin got in the body. It could take a week before we even start to see the first antibodies show up in the blood supply. It can take 2 weeks before we really are starting to get the maximum number of antibodies in your bloodstream. And depending on the toxin that gets in the body, tetanus is not a great one to get in the body. This could be deadly, or at least you're going to be hospitalized for it. However, if you're exposed to the toxin again, you now have memory cells to it from the first exposure. And you can start mounting a stronger immune system, so faster antibodies and more of them in a much faster time period. Now you've got full immune system response within 3 days versus 15. And again, you now have that immunity. You have memory cells that remember that toxin and can make those antibodies within days versus weeks. That's where we get into immunity. This is called anamnestic response. Now, if I take off the AN, ignore it's on my hand, what do you think of when you think of amnesia? If someone has amnesia, what happens to them? They forget everything. And if you stick A or AN at the beginning of anything, it means not or without. So it really interprets to not forgetting, which is a fancier way for saying what? Remembering. Why don't we just call them, it's a memory response, or also more officially known as anamnestic, or not forgetting response. It's a memory response. We have memory cells. We remember how to fight that pathogen off. Now, my big picture again, adaptive immune system. It's on the board. You have, the adaptive immune system's got B cells, your humoral branch, you've got cell-mediated immunity, you've got T helper cells, cytotoxic T cells, and those regulatory T cells that kind of monitor everything. Your immune system also has the innate immunity. That was the recording. Again, all the things your body was just born with. I've got this link. I think it's on your PowerPoint. You have the link on the bottom of your PowerPoints? Awesome. I think it's like an 8-minute video that's a nice summary of the immune system. And usually students are like, oh my God, so I just had to watch 8 minutes instead of like 2 hours. It's not as comprehensive, but if you're just like, I have no idea what she just said today or last Wednesday, and I don't remember anything from the video, it is still a nice, put it all together video of how the immune system works. Since we've talked about immunity, because this again feeds right into that chapter 17 PowerPoint, we group different types of immunity. We call them different things. So there's naturally acquired immunity and artificially acquired immunity. And the process of immunity can either happen actively or passively. Now, naturally acquired immunity means you have immunity to something you acquired in your everyday life. And I'm going to give you an example. So you've acquired immunity, so you have immunity, to something you've picked up in your everyday life. Artificially acquired immunity, so you have immunity, still immunity, to something you've acquired or have been exposed to via a vaccine. Now, I used to, back, even 10 years ago when I started teaching here, it used to be like a half and half, and I know it's not that anymore. But I'm going to have you raise your hand if you have a naturally acquired immunity something versus an artificially acquired immunity something. Now, naturally acquired immunity, again, this means you have immunity to something that you picked up in your everyday life. How many of you have a naturally acquired immunity to the chicken pox? It's like a few of you. That means at some point you've had what? You had chickenpox, which means everyone else that didn't raise their hand, you probably have immunity via what? You have a vaccine. I was going to say back in my day there was no vaccine because it's a relatively new vaccine in the market of vaccines. So naturally acquired immunity. So I had the chickenpox when I was a kid. I have immunity to chickenpox because I had it. That's a naturally acquired immunity. Artificially acquired is you got a vaccine. You didn't encounter the chickenpox. You were given some type of antigen against that virus, and you now have immunity against it if encountered in the future. Now, we can develop immunity or have immunity either actively or passively. And again, so it rolls right into the next PowerPoint because it's like a review. And active immunity means your immune system, like your immune system made the antibodies to cause you to have immunity. So you did all this. You activated B cells and made plasma cells and made antibodies. Your immune system was very active. You made the antibodies. Immunity is you have antibodies that were made elsewhere. And I'll give you a couple examples. Because people can have immunity because they're given antibodies that were made ever somewhere else. Super common example of passive immunity is nursing infants. They have antibodies in their body, not because they made them, is because they acquire them from the antibodies found in breast milk. So they have a passive immunity. They have immunity because they're getting antibodies in the body, but they didn't make them, so it's a passive immunity. And as soon as they stop nursing, they don't have antibodies going in. Antibodies don't last very long. That immunity will go away. But for a short time, they do have immunity. They just didn't make the antibodies. Another example of a passive immunity is, for example, is if you went out hiking and you got bitten by a venomous snake, or a snake you think was venomous and you went running to the ER. Your immune system, we have B cells that can recognize all the types of venomous snakes. We can recognize snakebite venom. We can activate those B cells. They can turn into plasma cells, and we can turn out antibodies to fight off that venom. But how long does that take? Too long. Maybe 2 weeks. If you were bitten by a venomous snake, do you have 2 weeks to wait for this to happen? No. So what do they give you? Antivenom. And guess what's in antivenom? Antibodies. We can give you antibodies that can then recognize that venom, bind it up, target it, make it, non-destructive, neutralize the toxin to save you. This was also one of the big therapies post-COVID. People that had a really bad reaction to the COVID virus, what did they give them? They gave them antibodies that were specific. They were generally harvested elsewhere. Someone else that made them and gave antibodies that could then target the virus. I'm like, sometimes, although your immune system can do this, if you have a working immune system, it takes too long that we can give someone antibodies as well. This is showing some examples of active versus passive. Naturally acquired immunity, yeah, you get something, you develop a full immune system response. Passive, natural acquired, mom was exposed to something, antibodies passed it on. Artificially acquired, again, anything artificially acquired is via a vaccine. Active, we're expecting your immune system to recognize what's in that vaccine and do all of that. Artificially acquired passives is if you were given a shot of antivenom. Is there's antibodies in there via a vaccine that you now have immunity. Kind of just smushing the words together. Now, I'm still going to start our next chapter because that actually reviews literally just that. The chapter 17 with a little bit of 15, they kind of start to blend together. Is now that you know how the immune system works, what are the types of vaccines out there? And how can we use our immune system response to test people for certain diseases? That's the chapter 17. I got to open it up. Now, we did finish this PowerPoint, so what's due before I see you next class? There's a quiz. Ooh, that looks newer. I wonder if there's pictures. Ooh, cool. So chapter 17 is taking everything we learned generally of the adaptive immune system and applying it. So it's all about immunization and immune system testing, so different types of tests. So again, it's like a review. It's like, what's the difference between active and passive immunization? We just went over it, but we'll review it again. And then different types of immune system testing. So we're going to talk about different types of vaccines because not all vaccines are created equal. So this, I'm like, I wrote the definitions in there, but you guys just defined them probably on your last part. An active immunization. So you're administering antigens to the patient via a vaccine, and it's active so that the patient develops or mounts a full immune system response. Again, it's active immunization. Is we're giving you antigens so that you mount an immune response against it. Passive immunization is you get immunity because you're given antibodies made somewhere else. And sometimes those antibodies are made, I was going to say, well, that's mom to infant, but sometimes antibodies are made in other animals. Not all antibodies. If you were given antibodies against something, they weren't all made in humans. Humans are not just big, huge antibody factories. I mean, we do that, but we're not going to make lots of people sick. I'm not going to give someone a snake bite venom so that they can develop antibodies against it. Sometimes we do give them to other animals, and animals have immune systems as well. This is just showing examples. Polio vaccine and measles vaccines. As soon as those vaccines came out, it's shocking, the number of cases went way down. Now, I want to draw stuff. I don't know if I need this up here or not. Different types of vaccines. Again, not all vaccines, when you're given a shot, vaccines are all not created equal. There are different types. The first type of vaccine is called an attenuated or a modified live vaccine. Now, when I compare my vaccines, I do it with smiley faces. So this is an attenuated or a modified live vaccine, which means what they give you, what they put into your body is a living organism, but it's not smiley face. It's, I'm not super happy face. It has a reduced virulence. It's not happy. It's not like the same exact thing. I'm not going to, in the COVID, which I don't want to use that because that's a whole different kind of vaccine. I'm like, if I want to make you immune to tetanus, I'm not going to give you tetanus. I'm not going to give you the bacteria that causes tetanus because that would be bad. But instead, I can give you something that won't cause disease. I can give you the living organism, but I've changed it. I've modified it. That's why it's called modified live, that it can no longer cause disease. Maybe I modified it so that this particular organism can't make a capsule anymore. And capsules are great for the bacteria, bad for us. So if it can't make a capsule, the system can recognize it, it can eat it and get rid of it, it can't cause disease. So it has a reduced virulence, aka can't cause disease. It has a strong immune system response. This is still a living organism in the body, and bacteria is going to do what bacteria do, and they're going to reproduce. And the more bacteria you have in the body, the more cells you're going to wake up, the stronger immune system response you're going to have. Now, it's also called an attenuated vaccine. Attenuation means I reduced the virulence. And sometimes they literally just UV radiate these organisms or some type of radiation. And I'm like, they didn't kill them, but they modified it so they can't cause disease. Problem is, it can still cause a mild infection. You still have a living organism in your body, and it can still give you a mild infection. So they can't cause disease, but it's still a foreign object in the body that's reproducing. That in itself can cause signs and symptoms, that there's a foreign object in the body. But what's cool about a modified live or attenuated vaccine is you have a living organism in the body. That in theory, you could actually, for a short time before our immune system gets rid of it and does its whole immune system response, you can actually spread that live organism to other people in very close contact. When I say close contact, it's usually like kissing someone, that this organism might be found in your saliva as it's in the body. And you can spread this organism to another person and actually their immune system. Now, it's a short window time period that has to happen, and it has to be close contact, but it can happen. It's kind of cool. Modified live or attenuated vaccines too. Pregnant women or people with a weak immune system. Pregnant women, it's still a foreign object in the body that can still reproduce. And because we're expecting strong immune system responses and because we don't always know and want to take the risk of how it might affect a developing fetus, we don't ever give pregnant women attenuated vaccines. And again, because we're expecting an immune system, strong immune system response, if you don't have a strong immune system and you have a living organism in the body, even though it can't cause disease, it's still reproducing, it can cause longer lasting side effects. So people with weak immune systems, we don't give attenuated live vaccines to either. An example of an attenuated live vaccine that maybe had, the flu vaccine has two kinds of vaccines, the shot and the nasal. The nasal is an attenuated live vaccine. The shot is inactivated or a killed vaccine, which means I've taken my object and I've killed it. That's how you make it killed. It's like get it like a whatever, lots of X's. But I can not only just kill it, and I call it a whole agent. So the whole thing's there. I've just completely killed it. Nothing alive in it whatsoever. But I can also take that killed object and I can break it apart. So there's part of my eye, there's whatever. It's all the parts. And I could put any of these parts, so here's the subunit. I can even put that little part of that organism in the body. The immune system's going to recognize that one little part. And if you ever get the foreign object in the body again, well, that part is still there, and it can mount an immune system response against it. So I've completely killed it, and you're either given the whole object that's killed, or you're just given a small part of the object that was killed. It's safer because there is zero chance that it will cause any kind of disease whatsoever. It can't reproduce. Completely dead. The problem is, it has a weaker immune system. Whatever was in the shot, that's all that goes into the body. There's no reproducing. The cell could at least grow and divide for a while. And I'm like, whatever is in there, that was it. Your immune system has to be able to recognize it quick, and it has to get rid of it, and it's not as long-lasting of a memory about it. Also, if you're just given small subunits, it's a smaller portion for your immune system to recognize. And so usually subunit inactivated killed vaccines, these usually require multiple doses. One shot is not enough. This requires multiple boosters. It's like, okay, well, we had a little bit of response. Let's bring them in a couple months later and let's do another shot. It's kind of just constantly waking your immune system up. One of the things that helps wake your immune system up are something called an adjuvant. An adjuvant is any kind of chemical that's added that increases the effectiveness of vaccine. Most adjuvants wake up the immune system. The immune system, it's not that it's sleeping, but it is just kind of slowly patrolling. An adjuvant is something that, when it's mixed in with the vaccine, almost wakes up and alerts your immune system that there is something here and you need to find it. I like to think of my coffee in the morning as my adjuvant. It's like what wakes me up and gets me going in the morning. It's kind of what wakes up the immune system and kind of puts them on high alert that there's something going on. I was going to say, I'm like, which examples? Diphtheria and tetanus are inactivated killed vaccines. There was, I found this somewhere and threw it on here. A subunit vaccine, again, just a tiny, instead of giving the whole object, which you could, let's just give you tiny little, fragments that when your immune system recognizes those tiny little fragments, it will mount an immune response against the fragments of something. No risk of infection, safer, but your immune system doesn't have as long-lasting of a memory. I mean, it's great. It's not the best, though. Toxoid vaccines it's not always the bacteria